Well, howdy, howdy, howdy. This is Unit 3. We're going to continue on, and today we're going to talk about the most up-to-date model, which would be the quantum mechanical model. We're going to start with talking about energy levels. Energy levels are regions around the nucleus where electrons are likely to be moving. This kind of falls in line with Bohr's orbit planetary model, except it has to do with probability. An electron can jump from one energy level to another by absorbing energy. And what we're going to learn at the end of this unit is that when energy is released from an atom, we call those photons. And what we're going to find is that photons can behave like particles, and they can also behave like energy, which is interesting. It's called the duality constant. Quantum is the amount of energy required to move an electron from one place to another, from its present energy level to the next higher energy level. So kind of like what Niels Bohr was saying about the planetary with the different rings and the different shells. Similar idea. Electrons are going to jump from one to another, and that amount of energy that it takes to do that is called the quantum. So you have different amounts of quanta at different energy levels. Atomic orbitals are the regions in space where the electron is likely to be found. A lot of people like to call these electron clouds. And there are several different shapes. Here we're looking at two. This is the S, and these are p orbitals. And there's 4 types, and we'll look at those in just a second. So not quite in your notes, but just a depiction of what we're talking about here. We're talking about the probability where we can find an electron. Electrons are moving all over the place. And so if we're looking at this image, let's pretend this is a still shot or a time lapse. At different points in time, we're going to find those electrons all over the place. But generally speaking, you'll see there is a spherical shape here, which is the most basic shape. And this is where we can find an electron roughly 90% of the time. We can describe electrons by 4 different quantum numbers. We must be familiar with these so we can identify elements based on their electron structures. Now, we're only going to cover 2 of them in this class, but we still need to be familiar with them. The first one is called the principal quantum number, which is designated with the letter N. It describes the principal energy level, and principal means where it starts, where the electron starts. The values can be 1, 2, 3, 4, all the way up to 7. The last row of the periodic table would be the last row. Now, I want to be careful with this one. You could say that the principal quantum number is just the row that the element is found in, but what we're going to find is that the rows actually change energy levels in certain spots in the tables. So I wouldn't just call it rows, I would stick with calling it energy levels. As we get bigger, as the periodic table grows, and we add more and more electrons, what we find is that in the different energy levels, which is this one, so this is our first quantum number N, this would be N equals 2, and this is N equals 3, the size, the radius of the atom gets larger, which makes sense. The atoms get bigger as we add more electrons. Number 2 quantum number would be the azimuthal quantum number. It is designated by the letter L, and usually it's a cursive L. It describes the shape of the atomic orbitals. S orbitals are sphere, P orbitals are peanut-shaped, D orbitals are daisies, and F orbitals we like to call fancy. L designates a sublevel. It basically talks about orientation. So you have an X, Y, and then you have a Z axis too in 3 dimensions. So what we're looking at here is the orientation in 3-dimensional space. The values of 0 up to and including N minus 1. So we actually associate these, and I would like you to write these in your notes if they're not already there. 0 is S, 1 is P, 2 is D, and 3 is F. Sometimes we use letters, sometimes we use the actual quantum numbers. So again, we have spherical shape, that would be 0 for S. And it would say L equals 0. And here we would say L equals 1, which is the peanut shape. And here is L equals 2, which is D. And we didn't include the F, which we will in a second. But if we look at how many orientations there are, there's only one orientation for the s orbital. There are 3 orientations for the p orbital, 5 for the d orbital, and if we were to look, F, which is L equals 3, that would have 7 orientations. So let's look at those. This is not in your notes, but just some extra information here. We have the first quantum number, and then we have our L, our second quantum number. 1s, 2s, 3s. It gets larger as we increase in energy level, but the shape remains the same. P orbitals, here we would have L equals to 1, and we have 3 orientations. Now it looks like these are all at the same energy level because they're the same size. D orbitals, again, these are all the same size, so we're thinking the same energy level, but we have 5 different orientations. 1, 2, 3, 4, 5. So this would be L equals 2 for D, and we could say that L could be -2, -1, 0, +1, +2. There are 5 different ways we could say that. And last, we haven't covered this yet, but F is the fancy orbital. There are 7 different arrangements for these. L equals 3, and you can have the orientation -3, -2, -1, 0, +1, +2, +3. So if we were to count those out, there are 7, and that's the third quantum number, which we're not getting into. But we call these fancy. We're going to go ahead and stop there today.